All right, so we're going to wrap up this section with a note about one-sided continuity or continuity at endpoints. So the thing is, when you think about your three-step definition for continuity, if I was to talk about, let's say, as an example here, let's say I thought about the function f of x was equal to the square root of x. And of course, we're all really familiar, I hope, with our square root of x function. Now, before this whole precise three-step definition conversation, I'm sure if I would have asked you, like, where is f of x continuous, most students would say that it's continuous on the closed interval from 0 to infinity. You would have included the endpoint. So if I had said to you, where is it, if I just asked the question, where is it continuous, you would have said, oh, it's continuous from 0 to infinity, right? And that would be correct. But technically, if you go through your three-step definition for continuity, if we don't make this kind of extra little caveat, so calculus, we're going to start to get a lot more precise with definitions, right? Hopefully you're already seeing that. So if you were to go through your three-step definition for, well, is it continuous at x equals 0? Well, you'd say f of 0 is equal to 0, that's good. But then you'd go on to the limit step, and the limit as x goes to 0 of f of x, well, technically, for the limit to exist, the limit from the left has to equal the limit from the right. Now, the limit from the right, as I get closer and closer to 0 from the right, I'm closing in on 0. But the limit from the left doesn't exist. There is no limit from the left. The function doesn't exist left of 0, so there can't be a limit from the left of 0. So that would actually mean that the overall limit wouldn't exist, and it would fail continuity at step 2. But that just kind of seems wrong because the function starts at 0, and then we just kind of draw from there after. So it just sort of feels wrong to say that. So essentially what we do is we just sort of define this one-sided continuity, and we basically just sort of say it's enough if the right side, so if you have a closed endpoint like this one on the left, it's kind of enough to say that you have continuity, you have what we're going to call one-sided continuity, as long as the limit from, like if you notice on this one, it was the limit from the right, right there, that limit from the right was existed at f of c. So then we'd be continuous from the right. And sort of the same thing then if you have a closed endpoint on the, like a closed right endpoint. So suppose I was to take, again, a similar function, the square root function, but let's just reflect it over our y-axis. So if I was to think about that function, it's just your square root function reflected over your y-axis. So again, as long as the left limit, which it does, exist at f of c, we would say we have one-sided continuity here. So it's just a way to define continuity just coming from one side. And so it just sort of makes more sense with what we would probably say almost intuitively here. I don't know if that comes up at all in the homework, but it's important to note. It's just important to note there. Okay, last little theorem here we want to talk about is something called the intermediate value theorem. We're going to kind of take it through one step at a time, and then we're going to kind of realize that the conclusion should seem pretty logical. So it says, let f be a function continuous on a closed interval where f of a and f of b are not equal to each other. Okay, so I think we can probably just draw in some function here in this first quadrant. So let's just say this is my function f of x. So here's f of x. And let's just suppose that this is my interval that we're interested in, let's say from a to b. All right, and certainly here, if I was to take a look at where those output values would be, this would be f of a, This would be f of b. They are clearly not equal to each other, so I think we're good so far. Then it says if n is any number in between f of a and f of b. So if n is any number in between these two values. So let's say here is my n. Then the theorem says there has to be, the conclusion is there has to exist a value c. So there must exist, there is at least one c in this open interval from a to b where f of c is equal to n. So the c that is guaranteed by the theorem is going to be from where this n, if I was to take it back, let's say to there, roughly, this value of c right here is what is guaranteed by the theorem. So as you look at that, it's like, oh, well, it seems, I don't want to say totally obvious, but it's pretty logical, right? So this is the c that must exist by intermediate value theorem. All right, so this is the most general statement of mean value theorem, and again, it's all about this existence of c. But typically, when we talk about this, there's going to be a subcase that we're going to look at, and actually, that's what I'm going to do here. So suppose that we take this, I'm just going to draw a straight line here. So now suppose, okay, so now we're going to take, this was my xy axis here, and now here's my xy axis. All right, so now what we're going to do is we're just going to essentially slide the f of a and f of b into locations where they're of opposite signs. So basically where one is above the x-axis and one is below the x-axis. So what we're going to see as we go from this picture to this second picture is going to be what I'm going to call a subcase, and it's really the most common subcase. I think if you have anything in your homework, it'll most likely involve this subcase of the intermediate value theorem. And so this subcase is going to say if f of a, if we make it just a little bit slightly different of a statement, if f of a and f of b have opposite signs. So the more general part of the theorems just simply says that they're not equal to each other. And so now we're going to say, well, let's make that into something just a shade different and say that they're of opposite signs. So again, let's just kind of attempt to draw, just a similar kind of boring type of function here. So here's my f of x. And so let's go ahead and just say maybe this is a right here. So this is going to be my value for a, which means this is where f of a is sitting. And then let's just say that this point right here is at b, and then of course this would be my f of b. So f of a and f of b are now of opposite signs. Then, if they are of opposite signs, that's going to have to mean that for our value n, that 0 has to be somewhere in between f of a and f of b, right? That if they are of opposite signs, then I can use 0 as my value for n. That has to be in between f of a and f of b. So what's the conclusion of the mean value theorem? Says that there has to be some point in this interval, some point c, where f of c is going to equal 0. So right here, there has to be some point c in the interval. So this is the value that must exist So specifically, we're saying what value has to exist? This point where f of c is equal to, and the specific value of n that we're talking about here is 0. Okay, so this is going to be your subcase of the mean value theorem that you'll probably be given homework questions about that subcase more so than the general case, if I remember. So let's just look at an example here. And so let's let our f of x equal 15x squared minus 22x plus 81. And suppose we're on the closed interval from -5 to 5. And so the question is, would the intermediate value theorem, I'm going to abbreviate IVT, allow us to conclude that there's a 0 in this interval from -5 to 5. Like, is there a 0 there, meaning an x-intercept? So this is definitely the subcase of the intermediate value theorem. Okay, so notice you're not actually being asked to find the 0. You simply want to answer, like, are the conditions there for intermediate value theorem to conclude that there must be a 0. So let's go through our conditions for the intermediate value theorem. So the first condition is that f is continuous on this closed interval. And it definitely is, right? It's just a polynomial, a quadratic, a parabola. So f is definitely continuous. Any interval I would give you, it would be continuous on that interval. So we've passed the first condition. Then for the subcase, we need f of -5 and f of 5 to not only be not equal, but we need them to be of opposite sign. So I'm going to save us the arithmetic. I subbed this in, and I had 566 for f of -5, and I had 346 for f of 5. So here's the thing. Because these are not of opposite sign, so because these are not of opposite signs, meaning you don't have one that's positive and one that's negative, this means that our intermediate value theorem can't allow us to conclude, or intermediate value theorem doesn't guarantee the existence of a 0 in this interval. Now, it's not to say that there isn't one. There could be, but intermediate value theorem doesn't guarantee it. And so that's all we'd say on something like that. Now, had those been of opposite signs, what would you go on to do? You would simply go on to find the 0, which would just involve setting that function equal to 0. It's literally just finding the x-intercept or finding the 0. Set the function equal to 0 and solve. Maybe in a case like this, it might involve like quadratic formula or something along those lines. But that's intermediate value theorem. Okay, so we're going to end section 1.3, and then when we come back next time, we will be in section 1.4. We're going to continue with these similar concepts, super important ideas of limits and continuity, but now we're going to bring into play our trig, exponential, and log functions. So they've been mysteriously missing in our conversation so far, and so we bring them back in section 1.4 next time.